Evening, good morning. Thank you very much for joining us for today's webinar. My name is Rob Fisher. I'm the Head of Sales and Marketing for SPI's online resource optics.org and of course all of their media portfolio as well. I'm very pleased to be joined by Simon Whitbread from Hamamatsu. Good afternoon, Simon.
Good afternoon, Rob.
Okay, so Simon is the X-ray technology specialist with Hamamatsu Photonics. Simon has worked for over 2 decades at Hamamatsu Photonics, where he currently advises UK industry in his capacity as an X-ray technology specialist. Having worked across all markets needing X-ray imaging from industrial security to medical and academic research, Simon has driven UK business development and managed a full sales pipeline for Hamamatsu Photonics. With a strong physics background, Simon can draw upon his many years of experience to educate and explain the principles of X-ray imaging to a wide audience, which is what we have here today. There's quite a few people that have joined us. So first of all, thank you very much to everyone that has joined us on today's webinar. I'd also like to thank again Simon for joining us as well. What I'm going to do is run through a few house rules that we have just to give you an update on sort of how things operate. With all of you, you should see a chat box in your dashboard or a question box. This is the opportunity for you to ask any questions to Simon during the actual webinar presentation. And what we'll do at the end, when we get to the Q&A, we will try and get through as many of those as we possibly can. If for any reason we don't answer your question, don't worry, someone from Hamamatsu will get back to you directly to follow up with you to answer any questions you have. It's also a recording, so if you miss any of the webinar, want to catch it again, or want to pass it on to any colleagues, then you can catch the recorded version of this webinar on the optics.org website in about 24 hours. Okay, what I'm going to do now is, Simon, I am going to turn my camera and mic off, and then I'm going to hand over to you, and I look forward to catching you at the end for the Q&A.
Perfect. Well, thank you so much for the introduction. It was much appreciated. So in my presentation today, I think I have 3 main tasks. The first task is to give you an overview of what industry in general may mean by inline inspection. How does that fit into the modern manufacturing line? And what's the expectation with regards to what you can inspect? The second is an overview of what's achievable with X-ray inspection. For some of you, X-ray inspection may be an imaging modality you are not so familiar with. So I'm going to go into a little bit of history and look at some of the fundamentals of how X-ray inspection works. The last of my tasks is to look at what Hamamatsu classes high-resolution imaging specifically with regards to X-ray inspection. High-resolution imaging can be considered a broad term, and as with many broad terms, what some industries class as high-resolution isn't necessarily the same as others. But for Hamamatsu and our X-ray inspection, we have a particular specialism that defines our understanding of what we mean by high-resolution imaging. And I'll go into detail and explain that to you. Once we've tackled all 3 of those individually, hopefully you can see how they can be blended together to produce inline high-resolution X-ray images, and therefore give you an understanding of the fundamentals of X-ray inline high-resolution imaging. So, first up, what is inline inspection? Inline inspection is used in many modern-day manufacturing lines as a way to control processes or identify faults in the products, or even more generally, to keep track of the product's progress through its manufacturing process. For today, I'm going to concentrate on 5 main industries which are manufactured in fairly automated environments and that Hamamatsu have a long relationship with. They are food production, printed circuit boards, automotive components, lithium-ion batteries, which are used both in electric cars and personal electronic devices, and specifically semiconductors with regard to chiplet modular designed IC chips. So using these 5 main industries, let's look into the types of issues that each industry could potentially be looking for. Firstly, for food inspection, typically they're looking then for foreign objects. These could be byproducts of the manufacturing process, or it could be a foreign object which have somehow fallen into the manufacturing line. There's obviously a safety and health and safety issue, making sure the food is fit for consumption as it's delivered to the consumer. But it's also about protecting the manufacturer's brand and ensuring the highest quality of product is supplied at the end of the day. For printed circuit boards, there are several items that can be inspected inline, such as faults on any surface solder joints. These can be inspected both visibly and by X-rays if the line of sight is blocked. Some inline inspections on PCs is used to detect whether or not there are any missing parts or any components which are misaligned during any of the reflow soldering processes. The automotive industry is obviously a very broad term, and there are many individual components which benefit from inline inspection. Tyres are inspected after the manufacturing process to ensure quality and ensure the lamination of all of the component parts have been done correctly. Engine castings are expected to ensure that there are no faults in the casting process, which could be a catastrophic failure while driving. Albeit the internal combustion engine is on its way out, there's still a requirement for metal parts which have been cast to be inspected to ensure they have integrity, strength, and will not fail when under load and pressure of everyday driving. Lithium-ion battery inspection has a lot of current interest, particularly due to the increasing volume of electric vehicles which are being manufactured and the upcoming phase-out of the internal combustion engine. Also, if you remember, a few years back now, some manufacturers of personal electronic devices had issues with batteries catching fire, as the component materials inside a lithium battery are quite flammable. So the type of thing manufacturers will be looking at is the gap between the anode and the cathode in order to make sure there is no short circuit or any foreign objects on the material before it's pre-rolled, which can cause punctures between the thin layers of the battery. Within the semiconductor industry, then companies may be inspecting for wire bonds or any voids within a ball grid array, which are used for bump bonding of ICs onto a PCB. For more modern chiplet designs, then the interconnects between the various subsystems are also of interest to be examined. So hopefully, just from these few slides, you can see the idea of the type of inspection which is beneficial for manufacturers in an inline process. And I've touched upon some of these using X-rays and imaging modality. But for some of you, X-ray inspection may be completely new. So I'd like to spend the next bit of the presentation just going over what X-ray inspection is and what's achievable. So firstly, let me give you a brief history of X-rays. Naturally, X-rays have been around since the dawn of time, but in terms of their use in industry, it was Wilhelm Röntgen who discovered X-rays while investigating the nature of cathode ray tubes at the end of the 1800s. This picture of his wife's hand with her fairly chunky wedding ring is a famous scientific image and is the first X-ray image ever taken. For all of his discoveries, he was awarded the Nobel Prize all the way back in 1901. People understood quickly the powerful nature of X-rays, and they were taken up extremely fast, both across medical and manufacturing industries. And within just 15 years of his discovery, there were over 100,000 X-ray tubes being produced every year. So although we've highlighted the 5 main areas of where X-rays might be used for inline inspection, today they are used almost daily. Across security, you'll be very familiar putting your bag in an X-ray machine as you board a plane. Maybe medical diagnostics for inspecting broken bones is something you have personal experience of. But also for medical, more high-tech imaging modalities like CT machines are commonplace for advanced diagnostics. They're also used for medical treatment. And in heavy industries, particularly, they are used to look at welds, where the integrity and safety of such advanced bonding processes are inspected. But why do X-rays have the properties they do? Very simply, in terms of wavelength, they are much shorter wavelength than the visible light, but because they have a higher energy, which enables them to pass through materials potentially without any interaction, and in particular with materials with a low atomic number, they are basically transparent. So we're all aware of the type of X-ray system I'm going to be talking about. I just want to let everybody know we'll be primarily talking about what we call transmission X-ray systems. This is where you have an X-ray source and a detector, but your sample is placed between the source and the detector, and it's the transmitted image that is collected in the X-ray detector. So, how does that work in reality? Principally, X-rays are able to do one of three things. They're able to pass through material unhindered, or they might interact with the material, either having their beam partially absorbed or some form of scatter away from the principal line of access. Or finally, if the beam is low enough energy, they can be completely absorbed within the sample. It's the combination of all of these factors which produce our final transmitted X-ray image. Another component of X-ray imaging I think is important to highlight is the effective magnification within a system. X-ray imaging, unlike visible light imaging, which uses potentially different apertures and lenses for a field of view and magnification, X-ray imaging is somewhat more simplistic, and the magnification that's achievable in a system is only directly affected by the position of the sample between the X-ray source and the detector. If the sample is placed halfway between the source and the detector, you will have a magnification of 2. You can think of it in the same way as you may have played when you were younger with shadow puppets. If your sample, i.e. your hand, is moved towards the detector while keeping the same working distance, your image or your shadow gets larger. Or if you keep the sample stationary and you move the detector away, increasing the overall working distance, you also increase your magnification. Likewise, it's good to understand how resolution is affected in an X-ray system from the detector side of things. The pixel size of your detector has a huge bearing on the achievable resolution. You can see here where we have a cross as a sample, but with a fairly coarse resolution detector, we end up with an approximation of that cross. Whereas if we double the pixel density, then we get a much closer representation of our sample. There is, however, a trade-off. With the overall sensitivity of our system, as the pixel size reduces, then the collection areas also reduce. So typically within X-ray systems, the higher resolution, the more consideration of an overall system signal or signal to noise ratio you need to be aware of. The types of detectors which are used in an X-ray system are typically linear detectors or 2D array detectors. And on this slide, we have a couple of example detectors. And I've highlighted with the yellow white lines where the active detection points of the systems would both be. Both types of detectors can be used for inline inspection, but linear detectors in particular have a nice advantage for inline inspection. As you can see from this slide, we have 2 sample images. On the left, we have a sample image taken by a 2D sensor. As the component runs over the top of a conveyor belt, you're able to see the X-ray image, but there's a fair amount of what we might call parallax or distortion to the image. But on the right, we have an X-ray image taken by a linear detector. As the sample passes between the X-ray source and the detector, we can see we might get a much better representation of the sample. In this case, it's the head of a lithium-ion battery. But because we don't have any parallax effects, we are clearly able to see the component parts without any distortion. So the third of our tasks today is to understand what we mean by high resolution. Well, to be honest with you, it depends on the application. Differing industries would class high resolution dependent upon either the foreign objects they're trying to inspect or the process control they're trying to examine. For food inspection, maybe it's typically between 0.2 to 0.8 millimeters. While it's nice to see small things, ultimately foreign objects or imperfections get so small as to no longer be a concern. For security, maybe this might be classed in the region of 1 to 2 millimeters. Again, objects which are smaller than this start to be of less of interest. For PCB and semiconductor, then the scale is considerably smaller. Typically, we're looking at 50 to 100 microns at the detector size, and actually the components might be even smaller than this. And it's handled by having a high degree of magnification in a system in order to see them clearly. With automotive or lithium-ion battery, then the resolution is probably the widest, as it really depends on the defined component which is being inspected. Typically, we see resolutions might required from 50 microns all the way up to a millimeter. In terms of really high resolution imaging and what Hamamatsu class as high resolution imaging, then it's the last two applications which are of most interest. So we've spoken about, in principle, how X-rays are produced. And we've talked about the trade-off between detector resolution and the requirement to have good overall signal level in your system. But it's worth spending just a little bit of time to understand exactly how they come produced within an X-ray source. Typically, X-rays are produced from the basis of what's known as a Coolidge X-ray tube, whereby we have a heated filament which emits electrons by thermionic emission, which is then accelerated towards a target, typically made of tungsten. And as the X-rays hit the target, due to the conservation of momentum, they produce what's known as Brahmstol braking. The radiation is a spectrum and is dependent on the acceleration voltage. The higher voltage, the harder it is to produce stable X-ray source, but the denser or thicker material you are able to image through. The target material also induces some characteristic X-rays, but as I've said, for industry, tungsten is such a common target material, these characteristic energies are basically always the same. Looking at a more detailed schematic of an X-ray source, you can see that the X-rays emitted from a target have an effective focal spot size, and it's this emission spot size which plays a really important part in high-resolution X-ray inspection. And it's this which defines Hamamatsu's specialism in the production of what we know as microfocus X-ray sources. The reason we need to produce this fine beam of X-rays is when we are looking at very small components which require high resolution. Unless we have the small focal spot size, we induce far too much blur into the image, therefore rendering any benefit we have from a small pixel detector obsolete. And it's the high resolution microfocus X-ray sources, which Hamamatsu specialize in, that are required for this inline high resolution imaging. We manufacture two types of sources, and they are what we call sealed type sources and open type sources. Commonly, a sealed source then is a reflection target, similar to the Coolidge tube that I showed earlier, with an integrated voltage power supply, which means that we are producing what we call a monoblock X-ray source. As everything is included in the block, there's no additional high voltage power supply unit, and there's no cables dangling around to get in the way of any systems or space considerations. We also produce what we call an open type source. Typically, these are transmission types, but not always. Then there is a metal vacuum column, which is kept under vacuum by a turbo pump. It has an electron gun with some focusing coils firing the electrons into our target, which is now a transmission target rather than a reflection target. The reasons somebody may want to use either of these types typically are down to the practicalities of everyday use. Inline inspection requires manufacturing lines to be operating 24 hours a day, 7 days a week. So whatever type of inspection process you have, you need it to be robust, stable, with little to no or ongoing maintenance. And our sealed type X-ray sources offer these features. Our open type sources, on the other hand, while they offer ultimately the very highest performance with regard to resolution and available energy, due to the maintenance cycle required, typically they are not used for inline applications, but they are sometimes potentially used for at-the-line inspection or normal failure analysis inspection systems. So let's have a look at our to-do list. We spent some time looking at inline inspection and what it means for industry in general with regard to quality control and process control. We've had a look at X-ray inspection, some of the history and the fundamentals of how transmission X-ray imaging works. And we've talked about what Hamamatsu consider high resolution imaging. And I hope you've got the point where you can understand why inline high resolution imaging is so important for modern day manufacturing lines with components with ever decreasing sizes. However, we really only covered some of the most simplistic imaging modes. And there are other types which require a little bit more technical software processing. We have oblique imaging, which is particularly useful for ball grid arrays to be able to look at different angles and maybe see voids which cannot be seen from the top-down view. Lithium-ion battery inspection, we can have inline CT, but maybe typically with a linear detector, as the field of view is maybe very small and a high speed is a requirement. We also have full inline CT with a 2D detector. Sometimes the sample is rotated fully, or other times potentially enough information is able to be gathered if the sample is only rotated by 90 or 180 degrees, dependent on the size and shape. We also then have inline planar CT, similar to the oblique imaging, but this is where the sample typically stays stationary and the detector is moved in a laminography style in order to collect enough data to produce a 3D image. Particularly with these 3D imaging modalities, with the advent of modern high-speed computing, it does allow CT to be done potentially in blind, but maybe slightly more commonly at the moment is what we would call at the line, with maybe a high number of sample of products are selected from every manufacturing batch, and throughput is done in an automated process, but just off the main manufacturing line. So across all of these modalities and the examples I've given, Hamamatsu is able to offer a wide range of products that can suit many different applications. We have an extensive range of monoblock style seal type microfocus X-ray sources, ranging from energy from 90 kV all the way up to 180 kV. We also have two specialized sealed transmission sources. These are particularly useful as they offer a compromise at the highest resolution imaging and the highest magnification, similar to our open sources, but with some of the added benefits of the long-term stability of our sealed type sources for specialist applications. Our open type sources then are run from 160 kV all the way to 300 kV, with the L10711-03 being our highest resolution nanotype X-ray source with an achievable system resolution down to 250 nanometers. We also have a range of linear imaging cameras, from standard single energy cameras, which benefit from high speed and low noise, to our dual energy cameras, which enables us to do some degree of material separation, or having a wide dynamic range. Typically, a dual energy camera is simply two cameras stacked on top of each other, one capturing the lower energy portion of the signal, while the other is detecting the higher energy portion of the signal. But for a lot of our high resolution systems, it may be our TDI line scan cameras that are the most interest to people, as the pixel size in these detectors can go down to 48 microns. And although I've not covered it in detail today, for those that may not know, TDI is a technology that stands for time delayed integration, and it is a way to have onboard signal gain within your detector, but with very little noise. And it offsets the trade-off, as I spoke about earlier, of sensitivity versus resolution. We're also able to offer linear components at the component level, such as photodiode arrays with or without scintillators, and potentially also with board level readouts. These are particularly useful if you are designing a system maybe with high space constraints, or of a system which has particular customization that a standardized subsystem detector isn't able to address. Then we have a range of detectors, such as our flat panel CMOS detector, offering high resolution with high sensitivity with a uniform response. And in the near future, when we have a more amorphous silicon-based detector with large areas and faster readout. We have our X-ray cameras based on our scientific CMOS in CCDs, and these have a much higher resolution than any of the detectors we've spoken about today, typically with a pixel size of 6 to 8 microns. But the trade-off is the field of view of these detectors is very much smaller, typically maybe only 13 millimeters. We also have some CMOS detectors which offer a nice combination of resolution and size. These have a resolution in the region of 20 microns. They can be compatible with pulsed X-ray sources, and the typical field of view then is 20 by 30 millimeters. So let's just have a look at our summary. Let's see what we've done today. we've had a look at what inline inspection is. It's a growing requirement for manufacturers to have a safety critical quality process. X-ray inspection is utilizing its unique abilities to see inside a product, providing a non-destructive inspection technique. And what do we class as high resolution imaging? We class those as imaging modalities that require the use of a microfocus X-ray source to maintain the highest imaging quality. So I've come to the end of my presentation. I'll hand you over to Rob in a second. But before that, I'd just like to comment on a couple of events that are coming up. Here in the UK, we have two events, Microelectronics, which is at the end of this month, and Advanced Engineering, which is at the end of October. Both of these will have some degree of our X-ray products on show. And over in Italy, we have automation and testing, which is also at the end of October. And you'll be able to meet with my colleagues to talk about any type of X-ray inspection technique that you may be interested to talk about. So Rob, back to you.
Excellent. That was a fantastic presentation, looking through a lot of the applications for X-ray detection, and certainly as a lot of the applications seem to be focused around sort of the manufacturing side of things as well. You know, and I think that is potentially going to become even more valuable when you look at things like photonics integrated circuits, and you know, there's kind of the level of complexity that's going to be involved as the semiconductor kind of expectations grow as well. So with that, we do have quite a lot of questions coming in, so I'm going to try and get through some of these as best we can. First of all, it says great presentation, so you know, much kudos to you. Why is open type X-ray source not suitable for inline inspection? Can you compare sealed and open types again? Thanks.
Yes, so one of the things, if I maybe scroll back on my presentation. Bear with me a sec, there's a particular, yeah, I think this is maybe the best line. So one of the things with an open type X-ray source is that you need some ongoing maintenance, typically maybe once every 200 to 300 hours. You will need to either replace the cathode, or you will need to change the target material. So if you're operating in a situation where you want to have fully automated inline inspection, where you have very little interaction with your system, then a sealed source, which might have a lifetime typically of even up to 25,000 hours or so, then between the two sealed type X-ray sources are generally the way forward for inline inspection.
Okay, thank you. We've had another question here, which also asks, according to common feedback, microfocus tubes are not dealing with 2 or 3 shifts per day. How do you deal with that?
I think it depends necessarily on the application and what industry that question is referring to. Within a processing line, which is then maybe 24 hours a day, which I think is where the question is coming from, then it depends really how the X-ray source is being driven, and whether or not it's a true inline or whether or not it's an at the line inspection, and exactly what's being inspected within the product. If you take let's say you take like a security application at an airport, then you know the X-ray sources are being run for many hours, potentially 24 hours a day, depending on the loading of aircraft, and a microfocus X-ray source is not too dissimilar.
Okay. Let's have a look here. So are X-ray inspection systems difficult to maintain?
Not necessarily, no. So one of the advantages of the sealed type X-ray source is that it's a standalone device. Once it's installed, you don't really have to do any ongoing maintenance to it at all. You can interrogate it via functions to check its performance and to check its maintenance level, but there is nothing actually that you need to do. And the same on the detector side. Silicon, you've all basically got pieces of silicon in your personal devices, and most X-ray sources, most X-ray detectors are silicon based, so there isn't any ongoing maintenance that really needs to be required on them.
Okay. I mean, you mentioned about installation. Are X-ray systems expensive to install?
I think it's fair to say they are considered purchases. An X-ray system isn't a cheap system, but the return on investment that you get on an X-ray system, I think, is very high. An X-ray system gives you the opportunity to inspect objects and products at various stages of their processes and make decisions on the quality, which allows you to have the benefit of making higher profit, making sure that your brand is protected. So the return on investment of an X-ray system is normally very high, despite the fact that the initial cost maybe isn't the cheapest.
Okay, thank you. Let's have a quick look. We have a few more coming in fact. Which type of X-ray detector are good for detection of a 0.5 millimeter gap?
So it depends a little bit then on the resolution within the system. So if the closer your sample is to the detector, then the more you're reliant on the, again, let me just scroll back to a particular slide. Yeah, so maybe this slide is the best slide. So the closer your sample is to the detector, the more reliant you are on the resolution of the detector. So if you are looking to have clear definition of a 0.5 millimeter gap, then but with little to no magnification, then you're probably looking at a 0.2 millimeter resolution detector. Whereas if there is a high degree of magnification, then maybe a 0.5 millimeter detector is okay, but it depends on the application setup in terms of where you can get your sample positioned between your source and detector.
Right, okay. And just jumping back as a follow-up from a previous question, if you don't recommend open tubes for inline inspection, how do you deal with focus pitting versus hours of use?
I'll be honest with you, I'm not quite sure what they mean by focus pitting. I've got an idea what they mean, but I think there's some various different terminologies. Okay. I think what they're potentially talking about there is if you have a X-ray source turned onto the target, kind of stationary, whether or not there's any target degradation. Okay. That's a little bit then control of the temperature of the target and the quality of the target to be maintained over a number of hours of use.
Okay. Okay. I mean, you get all the information of the people that are actually writing questions, so you'll be able to follow up with them directly after this presentation for sure. Is the resolution of detector dependent on X-ray energies? Sorry.
So the X-ray energy doesn't necessarily define the resolution in a system. The overall X-ray flux might have some contribution to the resolution in a system, as typically the X-ray sources with a higher flux will have a higher spot size in order to generate the overall X-ray signal. But the energy directly doesn't necessarily correlate to resolution, but the overall flux does have a component. Okay.
Okay. I'm just scrolling through. They're coming thick and fast at the moment, so you see, a lot to get through. So with regard to resolution, is the resolution limited by the focusing of the source or the detector?
So again, more often than not, it's a combination of both. It's a combination of both, really. So for a particular resolution on a detector, if there is too much of a mismatch between the detector pixel and the spot size from the X-ray source, then you might have some limitations with resolution. But you tend to find that the resolution of the detector kind of goes hand in hand with the X-ray spot size.
Okay. Is there a minimum size for a portable source and detector?
So Microfocus X-ray sources typically aren't portable. What maybe that person is talking about, this might be something to talk about offline, but there are portable X-ray sources, but they are typically not Microfocus X-ray sources.
Okay.
Portable X-ray sources might be used then for inspection of welds on pipelines, but they're in the field, in situ, in various gas or oil installations and such like.
Okay. We still have more coming in. So, oh, here's an easy one. Is the slide deck shareable?
Yes, it is, yes.
Okay. So if anybody does require or would be interested in receiving Simon's slide deck, if you could put a little note in the chat box, say me please, or yes please, then after this presentation, Simon will get all that information and he can ensure that you all get a copy of the slide deck. So that's an easy one. Let's have a look. Do safety concerns and shielding make implementation of X-ray inspection complex or expensive?
You do need to consider the safety aspect properly when you are putting an X-ray system in. Now, proper, accredited systems integrators will take care of that. The legislation between different countries are slightly different, and certificates and the names of certificates between different countries will always be slightly unique. But in principle, it is you do need to be aware of it. But as long as you're working with a reputable systems integrator, they will take care of that and make sure that there's no concerns for any workers on the shop floor as such.
Okay. So with regards to that, I mean, how long could you stand next to an X-ray source for? Is it, you know?
Well, I mean, if you think about a security line at an airport, the workers at those security lines are standing next to an X-ray source potentially for a full 8-hour shift. Okay. As you are walking, the shielding on those systems will be that is taken very seriously, so there won't be any leakage out of the system.
Okay. Okay. I think I've got time for one or two more, if that's okay. Yeah. Do X-rays harm the product?
Typically not. There is some, I won't say concern necessarily, but there is some investigation and work being done on some of the very smallest types of semiconductor materials, whereby you want to maybe keep the dose down to a minimum, but let's say for food, then X-rays don't induce any harmful byproducts in food inspection.
Perfect. Excellent. Cool. Okay. Well, I think we're going to wrap it up there. And I was just looking to see if we have any more coming in, but it looks like we do, but I think we're going to have to wrap it up there and then make sure we get you to reach out to everybody directly. Again, thank you, Simon, so much for your time doing a Q&A. There was a lot to get through there. And thank you very much again for the presentation. As Simon has mentioned, you can see everyone at Microelectronics next week. Where was the other one as well?
Let me just scroll down to the relevant slide. Whoops, as I've gone past. Oh dear, I've gone past. Put that on. One second. Oh, that one there. So we've got microelectronics at the end of September, advanced engineering in the UK, which is I think at the NEC, and then automation and testing also at the end of October with my Italian colleagues.
Excellent, excellent. Well, I will certainly be at Microelectronics next week, so I'll see you there. Also, I'd like to thank everyone that's watched this webinar today, and thank you for all your input and questions as well. It's been one of the best webinars we've had for a while, with interaction and engagement, and it always makes it a little bit more interesting. Again, you'll be able to catch this recording on the optics.org website in about 24 hours. If you've requested the slides, Simon will be able to reach out to you directly on those and get those over to you. And if we haven't answered your question, again, someone from Hamamatsu will get back to you directly. So again, thank you everyone for joining, and Simon, thanks very much for your time. I'll see you all on the next optics.org webinar. Thank you very much.
Cheers, Rob. Bye-bye, everybody. Thank you for your time.
Bye-bye.